Perfect, thank you. Yeah, perfect. Thank you very much. Okay, so I've also got your graded assignment ones here, and we'll collect assignment two up at the front. Thank you. Thank you. Right. Yeah. It's too late to ask one more question. Maybe. What is it? I guess it might be too late. I'm sort of stuck right at the end of the third question. Yeah. So I mean, I think what you want to make use of is if you have two components in parallel, it doesn't matter what they are. The voltage across them always has to be the same. And then if you have two components in series, whatever they are, they have to have the same current. So that's the tools or the information that we need for that particular problem. So the inductance, the voltage across an inductor is L di/dt, right? So that's what you would start with, and you'd say, okay, if I have parallel inductors, L di1 must be equal to L di2. That's the starting point. So eventually finding that inductors are going to combine parallel the same way resistors do, and not combine in series.
You're so close. You made a mistake somewhere, and I can't sing it. Oh man, I was really hoping you were gonna say it. You're so close. Keep going. You're so close. You made a mistake.
So assignments, with them going forward. Would your office hours be the best place just to get some?
Yeah, for sure.
Okay.
Yeah, that's what office hours are for, right?
Yeah, been running you ringer for a little bit. And start actually getting some of these. So.
Yeah.
All right. Well, if I made it that far, then I would. Like I got the right. Yeah. You know what? I feel good about that. Roll with it. And it's.
I really wish this had to happen at the same time the 3 midterms happened.
Okay.
I got 1 this morning, 2 later today.
You have 3 midterms today.
Today.
Oh, yeah, that's
Now
good.
it's like, oh, I totally, this slipped my mind that I
Yeah.
left the 2 last minutes.
Right.
It could have been better.
Yeah.
All right. So let's get started. If you haven't already noticed, assignment 1, we're returning over here and then collecting assignment 2 right up at the front. So thanks very much for that. So what we've been talking about is this introduction to complex numbers. And so far, we've just been purely mathematical about it. What I want to do today is I want to see if we can connect this to electronics. But first, let's just recap what we said. We said we could represent any complex number in 2 different ways. One is like a component form where we have like a real component plus j times an imaginary component. And then we began to imagine like maybe we could picture this in like a complex plane where the horizontal axis is the real number line, and then we have a perpendicular imaginary number line. And that looks a bit like a XY Cartesian coordinate system, where we're used to visualizing like our 2-dimensional vectors. And we know that we can also represent vectors using polar coordinates. And so we can do the same thing with our complex numbers. Instead of expressing them in terms of 2 components, we can express them in terms of a magnitude. And then it turned out this like e to the ij5. Okay, so we had some terminology. We had the real part of complex number z is just going to be everything that doesn't multiply to j. So x in this case. And the imaginary part would be everything that does multiply j. So the imaginary part is y without the factor of j. And then what we did is said, okay, let's think about our Fourier series, and we'll write these down for cosine and sine and the exponential. And then we ended up saying, okay, we have this series for the exponential. What if we put e to the x? What if we said x was equal to ij? And we did that, and we just round through it, and we found that it separated into the 2 series for the cosine and the sine. The sine one was multiplied by j. And so this is the famous Euler equation. E to the j phi is cosine phi plus j sine phi. Okay. When we combine those 2 things, we were able to find a way to go between the 2 different representations. So if I was given x and y, the real and imaginary components, I could calculate the magnitude and the phase. Or if I was given magnitude and phase, I could calculate the 2 components x and y. And that's basically where we got to. Today, what I want to do is I want to see if we can go on a little bit of an adventure and see if we can use complex numbers as a tool that will help us analyze circuits that are driven by sinusoidal signals. Okay. And the circuit that I want to analyze is the LRC circuit. and this is the one that you're gonna do in lab 4. So tomorrow, you're gonna build this circuit, but you're not gonna drive it with a sine wave. You're gonna drive it with square waves, and we'll look at the transient response like we did for RC circuits last week. Next week, we're gonna continue with lab 4 again. But this time you will drive it with a sinusoidal function. And so we're gonna start to work out some of the theory for this series LRC circuit today. All right, so how are we gonna start? Well, let's just start by doing a loop rule. So we'll go counterclockwise around the circuit, starting in the bottom left corner. And the first thing we do is we cross the input voltage supplied by our function generator. So we gain that, and then we're gonna cross the inductor, and then we're gonna cross the resistor, and then we're gonna cross the capacitor, and we're back to our starting point. So if we have the voltage supplied by the generator, and then there's gonna be some voltage dropped across our inductor, some voltage dropped across our capacitor, and some voltage dropped across our resistor, and then we get to our starting point. And that's just Kirchhoff loop rule. All right. Well, that means that Vn, if I take all the stuff with the minus sign to the other side, it must be equal to the voltage across the inductor. But the voltage across the inductor is L times di dt. And then we get plus the voltage across the capacitor. In fact, I'm gonna do resistor first. Let me do these in the order that they're written down in the diagram. So we'll have resistor and then capacitor. Okay, so then we drop some voltage across the resistor. Well, the voltage across the resistor is I times R. I'm gonna write that as R times I, just to be weird. And then we have plus the capacitor voltage. Let's see, capacitance is defined as C is Q over V. So the voltage across capacitor is Q divided by C. I'm gonna write that as 1 over C times Q. So this is the fundamental differential equation that governs the current in our LRC circuit. I don't like that we have current and charge in this equation. So what I'm going to do is I'm going to take a time derivative. So if I do that, I'm going to get the derivative of the input with respect to time. And remember, this is now a sinusoidal input voltage. So it's not a constant. So its time derivative is not 0. But anyways, what else do we get? On the right-hand side, we have L, and then we have to take a second time derivative. So it's 2 time derivatives of the current plus R times the time derivative of the current plus 1 over C. And then we have dq, dt. Well, that's just the current. And we've seen this second order differential equation before. This is what we solved, or this is what we tried to imagine what the solution would look like for the transient response, and we got those damped oscillations. We compared this to a mass on a spring. But we're doing something different now. We're not doing just turning the battery off and on. We have an AC signal. Okay, so what are we going to do? If we said Vn was some amplitude times sine omega t, when we took the derivative, we'd end up with a cos omega t on the left. And then we would assume the current is going to be some amplitude times sine omega t, maybe plus or minus some phase. Well, when I take 2 derivatives, I'm going to get a sine back again. When I take 1 derivative here, I'll get a cosine. When I take 0 derivatives, I'll get a sine. And so that's a mess, right? I don't like having sines and cosines mixed together. It's just awkward. So what we're going to do, this is the first trick. We're going to represent the
input voltage, which we would usually write as V naught sine omega t. I'm not going to write it that way. Instead, I'm going to write it as V in is some amplitude, that's the same. But instead of sine omega t, I'm going to write this as e to the j omega t. And let me just show you, if we were to use Euler's equation says we could write e to the j omega t as cos omega t plus j sine omega t. So you could kind of see that our original expression, V naught times sine omega t, is contained in here. It's the imaginary part, right? So we selected the imaginary part of this Vn. It would be everything that multiplies at j. We would get V naught times sine omega t times j. So the imaginary part is V naught sine omega t. So what we're going to do is we're going to represent our voltage like this complex exponential. We're going to do a bunch of manipulations. And then at the end, we're going to take the imaginary part, which will recover the original form of our input voltage. So we will do some calculations using this complex exponential representation of Vn, and it turns out we'll use that same sort of representation for I. Then, in the end, we take the imaginary part, which corresponds to our original Vn and yields the desired current. The reason this is going to work is because as long as I don't do things like squaring a voltage or a current, like calculating a power, if I just do linear operations, nothing's going to happen to mix the real and imaginary components. So everything I do to the imaginary part, which represents my actual Vn, I'm also going to do to the real part, but at the end, I just take the imaginary part as my final solution. So I'm carrying around some extra baggage that we're going to throw away at the end. But it turns out that having that baggage along for the ride is going to make doing these mathematical manipulations much easier, and I'll try to point that out as we go along. Okay, so we also represent the current we're trying to find as instead of, well, let's represent the current I is some amplitude sine omega t minus phi as I is some amplitude e to the j omega t minus phi. Again, if I take the imaginary part of this complex exponential, I'll get this original form. Whether we put minus phi or plus phi doesn't matter, we just have to make a choice. It turns out that the minus phi choice will make life a little easier near the end. And again, I'll try to highlight that when we get there. Okay, so what we have to do is we have to work with this differential equation. And what I'm going to do is I'm going to evaluate these derivatives using these complex exponentials. So we need to know things like d Vn dt. Okay, so that's d by dt and Vn. So instead of V naught sine omega t. I'm gonna write that as V naught e to the j omega t. Already, I like this because I like taking derivatives of exponentials because it's easy. You just get the exponential back again, right? This is just going to be j omega v naught e to the j omega t. But this v naught times e to the j omega t is just our vn. So what we have then is that this derivative is j omega vn. That's simple. If we were using the sine function here, that wouldn't happen because our sine would become a cosine. Okay, so fair enough. What else do we need? We need di dt. So same thing, we're going to write I naught e to the j omega t. This time we had a minus phi in there. Well, again, I really like taking derivatives of exponentials. I'm always just going to get a factor of j omega coming out. So we would get j omega I naught, and then the exponential will come back again. But again, whoops. This I naught times the exponential is just the current that we had. And so this is equal to j omega I. For the differential equation, we also had two derivatives of the current with respect to time. Okay, well, what's that going to be? That's going to be d by dt of j omega I, which is going to be j omega di dt. But we just worked out di dt. It was j omega I. And so we get j omega times j omega I, which j times j? Minus 1. So we get minus omega squared times I. Okay, so let's now put these results into our differential equation. Let's see if we can remember what the differential equation was. It was dvn dt was equal to L d2i dt2 plus r di dt plus 1 over c just times I. Okay. So the derivative of the voltage, j omega vn. All right, so we get j omega vn is equal to L times two derivatives of the current is minus omega squared L times I. Okay, minus omega squared L times I. Then we have plus R times one derivative of the current. So it's j omega R times I. So plus j omega R times I. And then it was plus 1 over c times I. So we're not going to do anything to that one right now. All right. I'm going to do one more little manipulation here. I'm going to divide by j omega. So let's divide by j omega. Okay, so if I do that, we're going to get Vn on the left. We're going to have minus omega squared L times I divided by j omega plus. Well, okay, this one's kind of nice. J omega divided by j omega just cancels. So we're going to get a R times I plus 1 over, I have to divide by j omega, so 1 over j omega c times I. Okay. So that's pretty good. I don't like the minus sign here. And so I can get rid of it. The way I'm going to get rid of it is I'm going to multiply this first term on the right by 1. But I'm gonna write 1 as j divided by j. So in the denominator, we'll get j squared, which is -1, which cancels the minus sign that I didn't like. So therefore, Vn is going to be equal to j. What else could we do? We could cancel one factor of omega. J omega L times I plus R times I plus 1 over j omega C times I. All right. Here's our first little bit of insight. What is I times R? Voltage across what? This is the voltage across the resistor. That's exactly what it is. So this is the voltage across the resistor. And this is our input voltage. Okay, well, what do you suppose the thing that involves inductance and current would correspond to? Voltage across the inductor, that's what it is. Exactly, this is the voltage across the inductor. And this one is going to be the voltage across the capacitor. Well, one of the lovely things that has happened is we love to write the voltage across resistor as current times something, the resistance. Well, we were able now to do the same thing for our inductor and our capacitor. Our voltage across our inductor is I times some stuff. The voltage across our capacitor is I times some stuff. Okay, so what we can say is for our resistor, the voltage across the resistor is IR. For our inductor, the voltage across the inductor is I times j omega L. What we're going to do is we're going to call this j omega L the impedance of our inductor. So this is ZL, which is the impedance of our inductor. Okay, and then we can do for our capacitor, the voltage across our capacitor is I 1 over j omega C, and we're going to call this 1 over j omega C the impedance of our capacitor. All right. So that's fine. What I'd like to do is that's a bit of a diversion. What we're going to do is we're going to go back to this expression here, and we're going to try to solve for the current. Okay, so let's see. If we go back to our expression about, we had Vn is equal to, let's see. Let's write j omega L as the impedance of our inductor, plus R, which is our resistance, plus 1 over j omega C as the impedance of our capacitor, and that all multiplies I. Well, if we go look at our original circuit, all the way back at the beginning, here we go. We have a series combination of components. Imagine that these were all resistors just for a second. Like this was R1, R2, and R3. If we had R1, R2, and R3 in series, what would we do? Combine them into one. And the way we would combine resistors in series is we just add them up. Well, what we've done is we have a series combination of an inductor that has impedance ZL, a resistor that has impedance R, or resistance R, and a capacitor that has impedance 1 over j omega C. And what we've got here is a series combination of these impedances, and they just add up the same way that, say, series resistors would add. So this is a series combination of impedances. And they yield Z is the total impedance, or the equivalent impedance in this case. It's just the sum of all those. Had we started with a circuit that had like a parallel combination of things, we would have found that our impedances added up to combine in parallel the same way parallel resistors would add up. So this is the net series equivalent impedance. Okay, so what does that mean? That means that the current is just V in divided by the impedance, and this is our first big result. And this should make you feel good, because if we had a circuit that had only resistors, we would say the current is just V in divided by, say, the total series resistance. So it's familiar territory in that respect. Okay, so let's see if we could make some progress. Let's now go write I is I naught e to the j omega t minus phi. That was our starting point. And Vn was equal to V naught e to the j omega t, like so. Okay. All right, so the equation in the red box becomes this for I is equal to Vn, which is V naught e to the j omega t divided by the impedance. All right. What can I do? I have an exponential of a sum or a difference. And what can I do with that? What's another way of writing that? Well, what I want to do is I want to write this exponential of a difference as a product of exponentials. Okay, and if I did that, we're going to end up with I naught the current amplitude, e to the j omega t, e to the minus j phi is equal to V naught e to the j omega t divided by z. Well, I like that a lot, because now I can cancel the e to the j omega t on both sides. If we were working with trig functions, these omega t's would be stuck inside cosines and sines, and we would not get this cancellation. So that's another advantage. That's the mathematical advantage of carrying around that extra baggage I was talking about, that cos omega t part of Euler's equation. Okay, so that means that I naught e to the minus j phi is V naught divided by z, this impedance. Okay, so what we're going to do is we're going to work on the impedance that we have here. So let's work on this impedance Z. So Z was the impedance of the inductor, which we said was j omega L, plus the impedance of the resistor, which is just R, the resistance, plus the impedance of the capacitor, 1 over j omega C. So what I mean when I say I want to work on this is, at the beginning, we said I could always write down any complex number in two different ways. I could write it in the form of x plus jy, and I can write it as a magnitude times e to the j phi. So I'm going to try to re-express this in the second form. So we want to express the impedance Z as an amplitude times e to the j phi, I'm gonna put a subscript z on our phi because we're already using a phi here, so this phi is the phi that's associated with our impedance z. Okay, so let's do that. Z is equal to what? Well, let me do this trick again, where I can move this j from the denominator to the numerator at the cost of picking up a minus sign. Okay, so z is going to be equal to what? Well, there's an r, so I'm just going to put the r there, and then I'm going to put plus j. Plus j. And then we have omega L from the inductor. And then we're going to have a minus from this j squared, 1 over omega c from the capacitor. Okay, this is now looking like x plus j y, where our x is r. That's the real part of our impedance. And y is equal to, well, let's see, it's omega L minus 1. And that one's a little more complicated, but this is the imaginary part of our impedance. Okay, well, we said I could write the magnitude of a complex number as the square root of x squared plus y squared. All right, well, let's see what that looks like. X is just r, so we get r squared plus y squared. Y is omega L minus 1 over omega c squared. Aha, okay. Now I'm going to be fussy here, and I'm going to say, look, this is correct, but I'd like to write it in a different way, slightly. My impedance is representing like something like a resistance. So I would like to see out front here something that's obviously in units of resistance. So I'm going to factor out the r from the square root. Okay, what would happen if I did that? I would say the magnitude of z is going to be, okay, I take r squared, maybe I'll take r squared out of the square root, let's say that. When I take it out of the square root, I have to take the square root, so I just get an r. And I like that. I like seeing a big fat r that's obviously measured in ohms out front of my impedance expression. So if I take that out, I get a 1 plus. Now, if I pull an r out here, r squared, I have to pull out r squared here. And so that means I would get an omega L over r minus 1 over omega rc, and that's all going to be squared. Okay, let's just notice something here. R times c. That's our RC time constant when we were talking about charging and discharging capacitors. So I know R times C has units of seconds. Omega is a frequency, it's inverse seconds. So the product, omega times RC, is dimensionless. I like that, okay? If you can work in dimensionless quantities, they often have some kind of physical significance to your problem. You just handed in an assignment where you analyzed the LR circuit, and you should have found the time constant L divided by R, or you said gamma was R over L, okay? So this has units of seconds times omega, which is 1 over seconds, and so this is also unitless. Yeah.
Sorry, just slightly lost. Where did that J go from?
Oh, yeah, we are just finding now the magnitude of Z, which is just x squared plus y squared. So the magnitude is always a real quantity, it doesn't have J. We still have to deal with the J, and we're gonna do that right now, okay? The other thing we have to do is we have to say that the tangent of our phase is equal to y over x. Okay, well, what's y? Y is right here, omega L minus 1 over omega c. So it's omega L minus 1 over omega c. And then we have to divide by x, but x is just equal to r. It's right there, so we divide by r. So we divide by r, and we divide by r. Oh, and look at that. The same thing that was inside the brackets of our square roots appears for this tan of phi. Okay, and so your question was, what happened to the j? And that's a fair enough question, right? Z was equal to x plus jy. And our other way of expressing this complex number is the magnitude times e to the j phi. So there's the j is going to show up in this exponential here, okay? And now we know these expressions for the magnitude of z is right here. So that's going to go into here. And the tan of phi is equal to this expression that we've written down. So if we wanted phi, we would say that's the inverse tangent of omega L over R minus 1 over omega RC. And that is what would sit here. Okay. All right. Let's go back to where we were. We were trying to work on this expression here. Let's give it a name. Let's call this number sign. Because now we've gone and we've written our z in a new form, and we're going to stuff that into number sign. So let's sub z is the magnitude e to the j phi into number sign. Now I have to be a little bit careful. What I said we were going to do is we were going to put a subscript z on this phi, so we don't mix it up with the other one. So it's right here. I wanted to have a subscript z on these guys. Okay, so what was number sign? Number sign said that, well, let's just go look at it. I naught e to the minus j phi. I naught e to the minus j phi is equal to v naught divided by z. But for z, I'm going to write this thing. Z e to the j phi z. Oh, okay. But this is v naught z e to the minus j phi z. And so I want to compare what we have on the left and on the right. The stuff inside the exponential, like the only way these two expressions on the far left and the far right are equal is if the stuff in the exponential are equal. They both have a minus j. And so that means this is valid or true only if phi is equal to phi z. And so therefore, the phase of our current in the LRC circuit is, well, we know that tan of phi z was, let me get it right. Let me not make a sign error. Omega L over R minus 1 over omega RC. Okay, So now the exponentials on both sides are equal. So that must mean the coefficients multiplying the exponentials have to be equal as well. So, and the other requirement is that this I naught must be equal to V naught over this magnitude of our impedance. And the magnitude of our impedance is inside that big red box. And so what we have is V naught. So divide by, there was a square root, but we had we have an R in front of our square root. I'm just gonna put that over here. I like that because this tells me that my current amplitude has the units of voltage divided by resistance, and that makes sense, right? That's amps. And then we had a plus, we had one plus, and then we had, let's see, omega L over R minus 1 over omega RC squared. And that is the amplitude of our current. So let's just finish this off, and then we'll go back and we'll do like a little summary recap of all of this. So let's return. Did we put a? Yes, I want to return to equation number sign. So let's return to number sign. Said I naught e to the minus j phi was v naught over the magnitude of z. Okay, so just for kicks, what I'm going to do is I'm going to multiply by e to the j omega t on both sides. Okay, so I'd have I naught e to the j omega t e to the minus j phi is equal to v naught e to the j omega t over the magnitude of z. We're going to use Euler's equation for these exponentials now. Now let's, so first, before we do that, we can combine these exponentials on the left as omega t minus 5. So now let's write e to the j omega t is equal to cos omega t plus j sine omega t, and e to the j omega t minus 5 is cos omega t minus 5 plus j sine omega t minus 5. And these are Euler's equations. Euler's equation allows us to do this. Okay, so that means I naught times, let's see, cos omega t minus 5 plus j sine omega t minus 5 is equal to, let's see, what do we have? V naught over z. V naught over the magnitude of z times cos omega t plus j sine omega t. Remember what we said at the beginning is we were going to write our voltage and current in this funny way because it was mathematically convenient. At the end of doing all of our manipulations, we were just going to take the imaginary parts, right? The baggage that I was talking about are the cosine terms. The part where we had V naught sine omega t, that's our input voltage. So we said that at the end of our manipulations, we would find our solution by taking the imaginary components of our results. Okay. Well, the imaginary component is the stuff that multiplies J. So we have I naught times sine omega t minus phi. But if you look at this, this is just our current. And that has to be equal to the imaginary part on the right, V naught over the magnitude of Z times sine omega t. So this is, I'm gonna write it this way. 1 over the magnitude of Z times V naught sine omega t. But this is exactly what we had for Vn. And so what we end up with then is that our current is equal to Vn over the magnitude of Z. Sorry, no, I can't do that. I can't do that. Sorry, I don't want to do this. Let me just leave it like this. Okay, so current times is equal to Vn divided by this impedance. But let's see, and we know now that the magnitude of Z, or let's not do that. Let's say I naught, sorry. I want to say I naught we worked out was V naught over R divided by the square root of 1 plus it was omega L over R minus 1 over omega RC squared. And the tangent of our phase was, well, it was the same thing that we had in the brackets underneath our square root sign. And so these two expressions fully determine the current in our circuit. What we'll do next time is we'll show that this circuit represents a resonator. And so it's going to have a certain frequency at which the amplitude of the current is large. And then away from that frequency, the amplitude will get small. And we also found that there's some frequency dependent phase. And so the phase will have a certain value at the resonance frequency, but as we move below or above that resonant frequency, the phase will change. So let's just do a little recap of how we started. All right. So we started by just drawing our circuit, and we said, look, I know that the current is going to have the same frequency as the signal generator, the function generator, but there'll be some phase shift. So my job is to find the amplitude and phase of this current. The way we did it is we started with really the most fundamental techniques we have for analyzing circuits. It's just a Kirchhoff loop rule. And that happened to lead to a differential equation. Now, here's where the complex numbers came in. We said, all right, instead of taking these derivatives of trig functions like cos and sine, let's take our input voltage and we'll add a bit of extra baggage, information we don't really need, but it's going to allow us to simplify calculations, right? The part we want is V naught sine omega t. That's the imaginary part. But we added a real part here, and using Euler's equation, we could write that as an exponential. When we write things as exponentials, the derivatives are easy and the time dependence ends up canceling out. That's the mathematical advantage, okay? Then we just took these derivatives and then we subbed the results back into our differential equation. And what we found is we were able to say the input voltage is the voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor. And we were able to express all those voltages as something times the current. That something we called the impedance. So for our resistor, the impedance is just R. If we want to, we could say the impedance of our resistor is just the resistance R. For the inductor, it was J omega L, and for the capacitor, it was 1 over J omega C. So then we could put that into our equation, like this really just followed from the differential equation. And we noticed that, oh, look, for our series circuit, our impedances just add the same way that series resistors add. From now on, we're not going to, every time we see a circuit, we're not going to do all this crap. We're going to say, look, I know that if I have inductors, capacitors, and resistors, that I can represent those all as impedances, and they're just going to add in series, or they're going to just add if they're in series, and they're going to add, their inverses will add if they're in parallel. So I'm not going to write down differential equations. I'm not going to take these derivatives. I'm just going to jump to a step that looks like this. And in fact, I could write down my current is just Vn divided by the total impedance, whatever that happens to be. And then the next step was to basically manipulate the impedance. And we manipulated the impedance in such a way that we could write it in terms of a magnitude times e to the j phi, or phi z we called it, which is this phase of the current. Is going to turn all of the information about the phase of the current is contained in this impedance. And so we're able to get these final results, and we're able to even show that at the end, if we take the imaginary part and get rid of the extra baggage that we were carrying around, we arrive at the solution we were trying to find. Okay, so what we're going to do next time is to prepare for the second part of lab 4, we'll analyze what these functions look like as a function of frequency. So as we vary the frequency, how does the current amplitude and the current phase change? Okay, after we've done that, we'll go back and we'll do some more examples of analyzing circuits that have these inductors and capacitors that are driven by AC voltages. And we won't write down all the extra steps. We'll just do the important step. We'll start by writing down the impedance, analyzing that impedance, and then saying we know the current will have the following amplitude and phase. Okay, good. Thank you very much. And we will see you. We got another freaking holiday. So Monday is no classes. I don't know how they expect us to get any work done when we're always on holiday, but nevertheless, that's what it is.